Thank you very much. We are still behind the schedule, so it's very challenging. Let's see. Okay. So we are behind the schedule, and this is 3:50 p.m., so this is biologically time for you to get sleepy. So let's see what I can do for you to entertain you. So in this talk, I'm going to talk about river. The content of this presentation has been partly made with my former student, Soo-hyun Yang, who is currently PhD student at Purdue, and also with Jong-min Byun, who was my former postdoc, who is currently assistant professor at Korea Military Academy. And this work has been supported by National Research Foundation. Okay, what's going on? This is not working. Oops, that's not working. Okay, so this very beautiful meandering river, which flows within very well-defined catchment, is a tributary of Colorado River. Just looking at this figure, the goal of this presentation is to share my perspective of river with you. And eventually, I want you to think about what is the function of river, and what's its dimension, and how it's organized. After this talk, I want you to think about the question by yourself. Do we know river? And what is a river? To give a hint, we can think about very simple cartoon. River can be seen as a connector between space and point. That area is a two-dimensional projection of a catchment, as we can say. Sorry, I don't have a highlighter, but that's two-dimensional projection. If you have a rainfall on that space, that will drain following that a line, one-dimensional line, which we call the river, and eventually reach a point. In that sense, we can tempted to say that river is one-dimensional feature that connects two-dimensional space to one point. Easily say that, but there is a more interesting story behind that. With this one, we can do a couple of interesting analysis. One of the analysis is to looking at the relationship between length of river and drainage area along downstream direction, like this way. As you start from the journey from the top of the river and following downstream direction, drainage area and length both increases. If you plot that on log scale, you will find straight line. In other words, power law, as you can see here. So we have two interesting questions from this plot. First question is, why power law? Well, because in many cases, physics, power law indicates scale invariance. In other words, something happens at very small scale is repeated at very large scale. Why that happens in river? And second thing is about its dimension. We know the dimension of this guy is length. And we know the dimension of this guy should be length square. For this equation to be dimensionally consistent, h should be 0.5. But if you analyze many rivers in the real world, empirically found that h is not 0.5, slightly bigger than that, actually around 0.6. So it's dimensionally non-consistent. Mandelbrot, a famous mathematician, has proposed very simple relationship. The dimension should be twice of the hex exponent h. So if the river is simply one-dimensional feature, h should be 0.5, and its dimension should be 1. But because in reality, river has bigger than 0.5 h exponent, we can say river has dimension bigger than 1. In this case, around 1.2. Sounds strange, because we are familiar with one dimension, two dimension, three dimension. But what do you mean by non-integer dimension like 1.2? We can explain that 1.2 means river is a little bit more elaborated than a straight line, but it's not really filling the full space like a two dimension. That's what rivers look like. So this is related to the concept of fractal, which Van Ding has already introduced. Well, that analysis is looking at river as just a single corridor. But in reality, river is a collection of all the passes. So it's an interesting story. So we have to look at the network feature. We have a very effective ordering scheme to effectively making systematic analysis of river network, so-called Horton Stroller ordering. The rule is very simple. we put the most upstream branches as order number 1, like these guys. And when the same order branches meet, each downstream becomes 1 order higher. So these guys becomes second order and third order. Using this scheme, we can find very interesting features for river networks. This is an example. So for example, you can count how many numbers of first, second, third order streams in this example. Well, of course, the number of first order streams are 9. We have 3 second order streams, and we have just 1 third order streams. And then you write these numbers and take a look at these numbers. We find very interesting relationship. This one divide this one is 3. This one divide this one is 3. So in other words, the ratio of number of streams between nearby order, we call bifurcation ratio, is almost constant, almost any river in the world. And this was first found by Horton and Horton's law. Horton repeated the same analysis with lengths. We call length ratio. In this case, numerator and denominator are switched. So this is also consistent. Later, Shum actually proposed similar analysis for area. RA called radar ratio is also consistent. This family of 3 laws are typically called as Horton's law. If the river networks follow Horton's law, we call Hortonian rivers, Hortonian trees. What's the relationship between number of streams or length area versus order? They will follow straight line on semi-log paper, like this or in this way. What kind of topological organization make it possible? The answer is the rivers are self-similar. Actually, Banting has helped me. He has shown a lot of pictures. So to make a long story short, if you take a small piece out of big catchment and make it zoom in, it should resemble the entire original catchment. That's self-similarity, which is key characteristic of fractal. So we can say river is fractal, has a non-integer dimension. We can find other families of Horton's law. One of the interesting eigenarea. The classical Hortonian method has inconsistency in terms of definition. Take a look at this third order stream as an example. I have highlighted second order stream, this first, second. When you define drainage area of a second order stream, this purple line. But when you talk about length of second order stream, that only covers from here to here. So there is inconsistency. While when you talk about length, that only talk about each individual segment, but when you talk about drainage area, it considers, it covers also upstream, higher, smaller order streams. So we can make it break down by considering so-called eigenarea. Eigenarea is net contributing area to specific order. So we can say instead of this entire A2, we can 2 A1s plus E2. Well, A1 can be also broken down into A0. A0 is essentially channel forming area or hill slope, and E1. We can do the E3 as well. By doing that, we can also think about how about making a ratio like this, like other Hortonian ratios, so-called eigenarea ratio. And the following question is this going to be constant, like Horton's law? To test this idea, we have done some real analysis for 5 catchments in Korea. And we found that, yes, they are following Horton's law. So we say there is a law of eigenarea. This is eigenarea. By the way, the other one is another Hortonian family law called so-called Tokunaga law. Because of time limit, I will just briefly skip this one. So for our analysis, these are 5 Hortonian ratios: bifurcation, length, area, Tokunaga, and the eigenarea ratios. You will find some interesting points here. First of all, RB and RA are quite similar. I will come back to that. But more interestingly, this new guy called RE and RL are almost identical. So we can easily explain this by defining RE following this definition. Each eigenarea has width times length of each channel segment. Width is basically overland flow length. Then RE is the ratio of overland flow length times RL. There is no physical reason why overland flow length should be dependent on the order. So we can almost constant, then RE is essentially the same as RL. Coming back to this fractal dimension, we said that fractal dimension, so-called ds, is twice of hex exponent. Following studies has actually expressed the same fractal dimension using Hortonian ratios like that. Well, these are perspectives looking at river as single corridor. But as I said, rivers are branching structure. So where this fractal nature is from? We can say that mostly this fractal nature is because of very minute meandering patterns. If you look at river in a different view, fractal feature also come from branching structure. So we have another fractal dimension called dB. And this is also represented as ratio of given a function of Hortonian ratios. Combining these two, we can actually get the relationship between Hortonian ratios given and like that. Well, what about real fractal ratio? Because rivers both has meandering features at individual scale and also has branching structure as a whole. The real fractal scale probably the product of these two fractal dimensions, and this should be less than 2 because river is still not a space. It cannot fill the space. Well, if you can imagine a very special tree network where this dt, total fractal dimension, is 2, in theory, we can RA equals RB from that equation. But in reality, dt is slightly less than 2, so we can derive that RA is always bigger than RB, which can be proven from our analysis, also supported by many, many other studies. RA is always bigger than RB, but they are close enough. Maybe about 5 or 10% differences only. From all these studies, we can conclude that very interesting relationships between these Hortonian family ratios. RL and RE are essentially the same. RB and RA, they are not same, but similar. And this guy should be bigger than that. So in that way, we can say out of these 4 Hortonian ratios, if you have to choose 2, RL and RB bifurcation ratio and length ratios are sufficient to fully represent Hortonian trees. How this can be given as a graph like this one. So one axis is either RL or RE, the other axis is RB or RA. You can plot these 2 straight lines, which is extremes of fractal dimension of 1 and 2. Most river networks which we have analyzed and others analyzed are fitting 2 extreme lines. So that's one aspect of river. Let's take a look at different aspect of river. This is slightly different story, but interesting story. If you compare upstream, typical upstream of river, downstream of river, by the way, this is Han River, there are differences. Of course, the size of particles are different. Upstream is big, downstream is very small. So we see that there is tendency, so-called downstream fining. So given discharge increases in downstream direction, particle size d, it tends to be fitted as power law with Q with minus exponent P. Well, also you can see that river becomes wider. So we say that width is increasing along with discharge in the downstream direction. Also, interestingly, the slope is different. From our empirical experience, we know that upstream tends to be steeper than downstream. If you connect the line, you will imagine that along the vertical profile, river tends to be concave upward. That can be expressed as like local slope as a power function of drainage area with exponent minus theta. So theta will be called as concavity index in this context. So I focus on this concavity. Actually, this concavity has been central subject in geomorphology and geology over 100 years. And this equation is very popular. And this is just one of the examples showing that how S and area are well-fitted power law on log paper. Well, you may say that other power laws are expressing the variable as a function of Q, why this one is A. Well, we can say Q and A are interchangeable. More specifically, again, following the river networks, as area increases, Q is increasing, and that relationship can be also fitted as a power law, gamma exponent. Simply speaking, you can it's 1, but that's for annual mean flow. For the high magnitude flow, gamma is known to be smaller, like 0.7 or 0.8. So the question in geomorphology has been, what are the processes that concave profile? Long history, but they have figured out there are dominant controls along the river, starting from the most upstream to the downstream. Most upstream, debris flow dominate. But if you look at that side, that's almost hill slope. You don't see, rarely see permanent river or streams. So that's not really main area of interest. Just below that zone, we call bedrock incision dominant area. So what do you mean by bedrock incision? The figure is like this one. So you have river flowing over rock, but there is no material moving around. The river has been formed by carving such a solid rock over geologic time scale. So it's very, very slow process. If you go a little bit downstream, you have alluvial transport dominated region. That means something is moving around. A picture is like this one. Even though these particles are pretty big, boulders, they are moving around. So the process of making river between these two sections are completely different. And geomorphologists has found that, and they have derived many equations to understand what's the difference between these two. But surprisingly, theoretical studies so far has shown that the concavity index, in theory, for bedrock incision and alluvial channels are very similar. And the number is around 0.43. I'm asking you to remember this number quickly because this is pretty large. Okay, this is pretty concave. Here we hypothesize that this alluvial stream may not be one kind. From our engineer's perspective, there are two types of alluvial streams. Well, this is typical alluvial stream, which is referred to in the textbook, geomorphology. But we know that there are also this kind of alluvial streams. Both are transport limited, but the difference is the particle size. So particle size is so different. Its physical implication is that in this case, particles start to move, only your flow reaches certain level of threshold of motion, so shear stress. But in this case, many laboratory experiments, many civil engineers, pioneers has done in the last 20, 30 years, they didn't find very clear evidence of clearance of motion. So maybe it's unclear. So we have hypothesized that for this type of alluvial channel, which should be distinguished from that, we may be able to neglect the threshold of motion term. With that idea, we decide to derive theoretical concavity index of a fine bed alluvial channel. We use very standard Skoklich type sediment transport equation, where sediment flux is a function of discharge raised by power of beta and local slope raised by power of alpha. So there is no threshold term. W is width, D is particle size. And we use scaling relationship. The reason is we are interested in river at steady state, and we believe river reach fractal characteristic at steady state. So we use many number of power laws we find in steady state. One of them is width increase as a function of discharge, we use most recent study of Gary Parker and others for the with increase as a dimensionless number of discharge. This equation can be decoded as like that. And if you put this into that original sediment flux equation, you get this one. Now I plug 3 from the top. That is downstream finding. This is hex row. So x is distance in this notation. And this is area discharge relationship. You put those them and arrange all the terms, you can express sediment flux as a power function of length. On the other hand, when you talk about evolution of channel bed, we should talk about mass balance. This is standard Exner equation, and bed elevation change over time is a summation of tectonic uplift and plus flux imbalance in the spatial manner. If you think about channel as steady state, in other words, partial g, partial t becomes 0, I can get this simple relationship by putting all the power laws here. And just to recollect your memory that we have derived this equation before, and you put that here, and put the integration, we can get this one. This looks like something lengthy, but actually, if you switch x, the distance, with area, again using hex row, the well-known hex row, then this is nothing but the relationship between slope and area. This exponent is essentially the theta. So we have analytical derivation of theta. It says theta is function of alpha and beta. Those are driving parameters which about the evolution of system. Gamma is the exponent of Q&A relationship. N is width relationship. H is hex exponent. P is downstream finding exponent. These parameters are subject to variability. So each river has some range. So we cannot get deterministic one value per theta. Instead, we have made a collection of all these parameter values and run Monte Carlo simulations, millions of simulations. And the result is like that. So this is distribution of theta value. A very surprising finding is that the most frequent range is here, between 0 and 0.1. This is such a foreign idea because in classical rotation, alluvial channels set 0.48. That's way over there. But our analytical solution says that in theory, maybe, for the fine bed material, theta can be much, much lower. That means almost no concavity. But to prove this, we have to find real set. Have a look at real ideal experiments. The first experiment was so-called rainfall erosion facility. In 1970s, Colorado State University has built rainfall erosion facility and done a lot of experiments. They are not doing experiment anymore, but they left a lot of data. And we dig out the old data and find out the final evolutionary path and look at the concave profile. And the result is that the profile from that simulations, they use sand particles, by the way, is surprisingly similar to our analytical solution. So theta can be very small. But this is very small facility. What about real world? Well, real world, we cannot find real ideal setting in the mountainous regions like Korea. But we have looked at post-glacial system. So some latitude, there are some well-developed post-glacial system. Good examples are found in near Midwestern US, near Great Lakes, and also similar latitude, Northern European area. So we decide to analyze two rivers here, Minnesota River and Wabash River in Indiana, and two other rivers in Poland and Lithuania. Their longitudinal profiles are really flat. So theta value can be, in reality, so very small, like 0.07 or 0.01. So the message is that we have power laws in many angles of river networks, and we can think about there are still many new discoveries waiting our future generation, future scientists. So to wrap up this talk, I'd like to say first, rivers are fractal, either looking at them as a single corridor or as a network. They have a non-integer dimension between 1 and 2. This is different. If you say what is the fractal dimension of landscape, that should be between 2 and 3. Okay, I'm just talking about river. There are many quantities. One of them is very famous, legendary Hortonian laws. And one of them is eigenarea law, which was found very recently. But we say that out of many, length ratio and bifurcation ratio are two most important independent ratios. Fractal characteristics can be also represented by many power laws. They are not only in the network characteristic, but also particular characteristics such as profile. And by combining these together, we were able to derive the theoretical concavity index of fine bed alluvial river, which has very different concavity index. After all this, I want to ask this. So do we understand what is river? Thank you very much.